wrap up chapter 2 and then start a little discussion on chapter 3 before we have our first quiz, okay? So my plan for today is first we start by wrapping up chapter 2, and we're going to basically start with the model which has been introduced last time, and use these models and do simple circuit analysis. So just to give you a sense as to which model to pick and what is the tolerance of inaccuracy that you would expect. Okay, so anytime you use a model, there is a discrepancy, meaning that it's not exactly accurate. Anytime you use a model, there's an inaccuracy. There's no 100% accurate model. It's just the tolerance to the accuracy. Okay, so we're going to talk about different type of model and what type of error you will expect in these type of calculation. And then we're going to talk about, of course, entering chapter 3. We're going to start using the model that we have established, either exponential model or the constant voltage model. Those are the most commonly used model for large signal analysis. So we're going to do something, we're going to introduce the idea of basic circuit analysis, go through maybe a few examples to give you a sense as to when there's a diode in your circuit, how does one approach in analyzing these characteristics. Mostly we call it transfer function. We're going to talk about this a lot in introducing the concept of large signal analysis and small signal analysis. I'm always using the analogy is that if I'm doing a transfer function or in a large signal analysis, meaning that I'm exploring the stage from this end to that end, okay? But if I'm standing at a particular point where I'm just doing the performance in a very small region, that's called a small signal analysis. So we're going to break that down into these two types of analysis, so you get a sense as to what is the point of the circuit operation or signal processing in a circuit. How does these two types of analysis affect the procedure as well as its performance? Okay, so we're going to briefly go through this, and then probably next week we're going to start really talk about rectifying circuits and its impacts. Okay. So these are the things I hope to cover today. Before we actually go into the circuit part, I'm going to just briefly review because a few of the students asked me these questions, so I just want to clarify this, clarify these parts in the discussion of diodes. So there's two important things, is that when you have a depletion, either is this can work for either equilibrium, reverse, or forward. These are all true. So what happens is that if you expect there's a depletion in your PN junction, so there will be depletion charge right at this junction. Therefore, this charge would then create an internal built-in potential or built-in electric field. This electric field, the slope itself is proportional to depletion, the charge density. It's a charge density rather than the net amount of charge. But the field at the peak point will depend on the total charge, whether it's this side or that side. It's actually the same. The area here equals the area here. So these two are identical, right? So the peak level here will depend on whether this side or the other side. The net charge on the block, you can see that the area of this blue square or the area of the red square is the same. So the electric field at this junction, x equals 0, has the maximum electric field. The field depends on net charge on either side of the junction. But the slope itself will depend on the density. Okay, so there's a difference. So if I expect you to draw a line, for example, if I'm increasing, for example, if I'm making this looks like similar, both sides are about the same, right? So if I'm making, for example, ND, I say 100 times larger than NA. I'm just increasing ND to 100 times. What do you expect this curve will look like, or the shape will look like? So I'm not going to give you the answer. You can do the exercise on your own. It will be very offsetting, and typically we refer that as one-sided junction because you don't actually see depletion on the other side because it's very narrow. So you should be able to do some exercise on doing the plot when there's changes in doping concentration. How does it affect depletion? How does it affect the shape of your slope? How does it affect your distribution of electric field or potential? Okay, so you can do the exercise on your own. So what we're going to do today is actually entering the circuit part. We're going to do this maybe 2 or 3 times in this class because we're going to introduce this device itself and then use the model and enter the circuit analysis part. So we're going to just forget all the depletion that what happened inside the physical, or I should say the physics of devices is not essential in circuit analysis once you have the model. So let's talk about how do we bridge the model into circuits and then do some simple exercise. So this is a very simple example. I wanted to give this example and then ask you to use different type of model and the parameters given to you to find the key performance factors in the circuits. So what we're going to find are 2 things. We're going to expect you to find the current under different bias condition, and also if it's reverse bias, we're going to talk about is capacitance, junction capacitance. So ask you to find Ix and Cj under, this is only, Cj will only consider under reverse because in forward it's very hard to determine. So I want to find this under Vx, let's say minus, let me get it a number, 2.7 volt or 1 volt or 3 volt. Okay, so I want, the question is to find these speeds at these 3 conditions. So let's look at part, so this is part A. I should say, and using either models, so if you use model A or model B, determining on the biasing condition. So there's model colorings of that. This is model A, which is the exponential model, and this is model B. So determining on which model you use in determining these, to find these parameters during the operation. So first of all, let's start with first part is when Vx equals to minus 2.7 volts. So I'm giving you particular numbers because this is actually easier to analyze. So the reason why I'm using this is that because when I'm applying a negative voltage across this 2 terminals, you will expect your diode will be in reverse. Therefore, your current Ix, you can use the exponential model, but Ix will actually equals to Is, I should say, minus Is, so which is minus 10 to the 16. It's a very low current, right? So even though you can actually ignore whatever voltage drop is on here, it doesn't really matter because you're turning it off. So because this is really in reverse, we want to find out junction capacitance. So we're going to use the junction capacitance equation, which is Cj0, 1Bo. If I'm using Vd instead of the positive voltage, so this Vd over Vo. Okay? And Cj0 is given to you, this is given by model. This is a very, very low level. You have to understand that this level is per micron, is only femtofarad. So this is a very small capacitance. in the overall integrated circuit system, this is a fairly low capacitance per unit area. So this will give us 0.26 femtofarad per microfarad. And this will be 1 minus 2.7, and we know that the doping potential is about 0.9. So that will give you a minus 3, so that will be a square root of 4. That's why we get about 0.13, about 1/2 of the, if you're on the reverse bias, you're getting about 1/2 of its value under equilibrium. So the capacitance is even lower because depletion grows and the distance between charges increases. Okay? So this gives us the first part. There's essentially no current. You don't need to consider voltage drop across here. It doesn't make any sense. And the current is in reverse saturation. Therefore, it's minus IS. Does not change too much. Okay? And this constant voltage model doesn't work. If you're using constant voltage model, this IS will simply be 0. But you don't actually care because if you give me the number 0 or 10 to the minus 16, it's essentially the same for most of the circuit consideration. Okay? So let's move on to part 2. So how does one solve part 2 when you're applying a voltage Vx equals to 1 volt? Okay, we can either use model 1 or model 2. So let's look at model 1. How does one approach this problem? You start with a KVL. So we start with Vx equals to what? Equals to the voltage drop on the resistor, which is IXR1, plus the voltage drop on current. So, on diode, sorry. So let's remember our exponential diode current equation is ID IS exponential. Exponential VT minus 1. In this case, we expect our current, or this is much larger. Typical operation, this is much larger than 1. So this equation can be simplified as ID exponential. You just skip the 1. So how does one express your voltage drop on the diode? You want to, so this is VD. But you want to express VD as a function of IX. So this will then become IXR1. And simply finding out VD. So VD is VT ln the ratio between current. ID is IX, right? The current flowing through the diode is the same as IX. It's the same. So it's IX over. Okay? So this is given. I already give you this is 1K. This is a nonlinear equation inside natural log. So you can just dump it into a spreadsheet or MATLAB, that sort of things. This is given. We already know these two, so then we can solve for and this is given, so I already know these. So for example, this is 1 volt, this is 1 k ohm, and this is 10 to the minus 16. This is 26 millivolt. So in this nonlinear equation, then you can actually solve for Ix. Let me get the answer. I think I had the answer, but I don't remember. Okay. So if you actually go into and solve this nonlinear equation, it cannot be solved by hand, but you can do some sort of iteration. If you do some guessing work and do some iteration, you can actually approach the answer. We'll talk about that a little bit later, but through iterations or softwares, you can actually find that Ix is about, okay? So this is one way of solving this. The other is, of course, using the constant voltage model. So let's look at how we're going to do it. So part 2 is when Vx equals to 1 volt, but we're using constant voltage model, CV model, where anytime you see VD on. So in this class or in the following exam or quizzes you're going to take, if I give you IS, that simply implies that you use exponential model. If I give you VD on, you simply use constant voltage model. So if VD on is given to you, VD on equals to 0.8. So we're going to also do this analysis. It will be much easier without this complicated nonlinear equation. Is that you start assuming, we know that the device is turned on, D1 is on in this circuit, in this setting when VD is equals to 1. So your circuit, well then your equivalent circuit will become this. We're simply substituting this. So this would then be your equivalent circuit. Right? This equals to 1 volt. Okay? And VD on is 0.8. So what we want to do is to find Ix. So here it will be very easy. Your Ix will simply be Vx minus VD on divided by R1. And this will then give you a current of 0.2 million. So you actually see that if I'm doing it precisely following this model, it will give me a more precise current. But this will give you, in the ballpark, very close, but you accept you accept maybe 10 to 20% inaccuracy. We're going to actually do this very quickly with Vx. If I'm changing part 3 Vx to 3 volt. What happens is that you can still use A or B. Let me do the B first. Let's do the B part. B meaning that it's, so this is part B, where we're using constant voltage model. So if you increase your voltage to 3 volts, this will be very easy. If you're using constant voltage model, your current Ix will then become 3 minus 0.8 divided by 1K. So this will give you 2.2 million. We can also do this using exponential model, and you simply insert it. It will be 3 volt Ix 1K plus 26 millivolt ln Ix 10 to the minus 6. So simply change the equation by simply changing this. And you can also get an answer. The answer is so what happened is that it's not going to be exactly 2.2, but very, very close. So that means that if you're at a higher current level, this approximation is actually much more closer to your real answer, the constant voltage model. So there's a discrepancy what depends on the biasing condition and the applied voltage. So a different model will then give you different accuracy level. So you have to be aware of that when you use these type of models. In this class, it's probably fine because we're going to tell you which model to use. But in the future, every time you use a model, you have to understand there's a level of tolerance. different type of model and what it implies. But I'm just going to tell you that for diode circuits, for chapter 3, we're not going to use this model very often. It's probably in chapter 2 you will use exponential model. In chapter 3, we're probably going to just stay with constant voltage model in most cases. Okay? Okay. Any questions on chapter 2? So we're going to move on to chapter 3. I'm going to start. Any questions? If not, let's move on to what circuit analysis methods and what are the key important factors. So in chapter 3, as I said, we're going to start talking about we're going to introduce you a concept of, we call it transfer function. The first topic, I should say. What is a transfer function? Is basically if I'm having a circuit, a black box, and if I'm giving you an input, I'm looking at the output. This is typically referred to as a transfer function. If I have a circuit, or whatever input I'm giving you, the external output performance. So let's say this is my input level, this is my corresponding output level. And most of the amplifier you're looking at, it will be something like this. If it's an amplifier, it will look something typical characteristic of amplifiers. It amplifies at a particular range, and then it might taper out at a certain level. So the line in yellow is we refer to as the transfer curve or transfer function. So this is the transfer curve. Or transfer function. So it's in describing the point of this. So the point of the transfer function, or sometimes referred to as the input-output characteristic. So you typically give a range of inputs and look at its output. That's basically what it means as a transfer function. So once you have the definition, I'm going to give you a few examples and ask you to generate the transfer function if you can. So we're going to go through 3 diode circuits. Since we already had experience of analyzing a diode, then you should be able to generate a transfer function. So we're going to use an example. In the following example, I'm just going to use the more easier for analysis. We're going to use the constant voltage model for the diodes. So these examples, example 1. We use constant. Basically, we're going to use constant voltage model as that particular cases. As I said, we're going to use constant voltage model by setting a particular VD on. And if we're operating in this range of current, it's typically in the range of 0.6 to 0.8. We're going to use 0.8 for the following analysis. So this will work for all the examples. We're going to follow the constant voltage model. Let me remind you again what's constant voltage model is that when your diode, for diode, when VD is smaller than VD on, we assume that it's open. Okay, so if VD is larger or equals to VD on, we're assuming that it just take on a voltage drop. So if you want to draw the IV characteristic of this model, would simply be 0.8, and it turns on. That's basically it. Okay? So using this model, we're going to go through a few of the examples. I'm just going to start with a one diode example. So this is my diode D1, R2, R1. And this is my input terminal. This is my output terminal. I have two terminals. One I want to look at its transfer characteristic. Okay? So first of all, typically what we're expected to deliver is something like this. It will depend on your operating range. So your input, there's a possibility of a voltage range is typically supplied by its maximum and lowest amount of voltage. So in this case, it's going to use -5. You're assuming that your highest voltage is -5 and lowest voltage. So you set the boundary first. So this is typically set by supply, power supply, or power supply range. Power supply range or the limit of your circuits. So in this case, we can use -5 to 5 for all the cases we study. Okay, so if you have a circuit, what you do is that you simply sweep. So you can give you a power supply, you sweep the input and observe the output. So you use a voltmeter and to measure the output, and you're supposed to be able to get the transfer curve. In this case, we're going to use it through our model. So how does one determine what happens? First of all, a good way of approaching this type of question is to start with the easy part where it's open, meaning that there's no current. When there's no current, it's actually much easier. So we know that if I'm starting ramping this voltage, you expect you start with -5. If I'm starting with -5, what do you expect? You expect this voltage will then propagate to here, this device will be turned off. So we expect that when Vin is smaller than medium, what happens is that if it's smaller than 0.8 volt, this whole loop is not on, meaning that there's no current. The diode current equals to 0. Therefore, if there's no current on this resistor or diode, there's no current here, there's no current flowing in. Therefore, your output voltage. Now let me first write, what is the output voltage? Being minus I, wait a second, this is I1. Let's say this is Ix. There's only one loop because your voltmeter does not take any current. So Ix equals to ID. Right? So this will be Ix R1. Because Ix equals to 0, therefore, what does it mean? VL equals to Vin, right? So that simply means that at 5 volts, VL follows Vin. Therefore, when this is 5 volts, this is -5, this will be -5. Right? It will follow it all the way to where? This is called the turning point. Because anytime it switches from different modes would experience turning points. So you set the turning point at 0.8 volts. So what happened is that I'm drawing this plot, it will then end at 0.8 it should follow itself, so this should be 0.8. Your turning point is 0.8, 0.8, because V in equals to V out when the diode turns off. There's no voltage drop. There's no voltage drop on resistor, therefore this point equals to that point. Good? Then we get a curve, a straight line all the way through the center into here. Okay? This is really straightforward, right? So let's look at what happens if it's higher than. So this simply implies V out equals to V in when V in is smaller than 0.8. This is basically what it says. So if we look at the second part, if we're looking at the second part, when V in, what happens if V in exceeds 0.8 volt? So in region 2, what happens when the diode turns on? When the diode turns on, your circuit will look something like this. You simply insert your model in. This will be R1, R2. This will be my VA. Right? This will then be your circuit. So based on this circuit, you simply insert this into your model and we'll be able to extract what V out could be. I don't have space. Let me use the right. Nice. So what happened is that your V out, after a certain operation, there's a voltage dividing because the current, let me do it slowly. So first of all, we find the current Ix. Once again, Ix equals to ID equals to V in minus V D on divided by R1 plus R2. Right? Voltage drop across these two resistors is written like this. So after rearrangement, and your output voltage is actually VD on plus R2 times ID. So you simply insert that back in, and we should be able to get an equation look something like this. This will be VD on plus R1, R2, VE minus VD. Okay? So you can actually get a transfer function either in plots or in equation. So this is the transfer function at region 1. This is the transfer function at region 2. And you can put it in curve. So let's give you a number so that it's actually easier to give it a curve. So this will be, let's say if I set R1 equals to R2, what happens is that my transfer function in region 2 will be 0.8 plus 1/2 V in minus 1. Okay? So what happens is that you will then actually see this. You will then flatten out with a slope of 1/2. This is the slope of 1. Right? And your turning point, the good thing is that you can actually get the boundary point as well. Just simply insert 5 and get the boundary. What is it? At this point. This will be 5. And this is, we know that this is 0.8. And this point is minus 5. Okay? So anytime if you're ever doing this in an exam or a quiz, will ask you to draw the transfer curve and give each point, the boundary and the turning point. You have to be able to find out where it turns and at a particular point. Okay? Okay, so if everyone is okay with a one diode system, we're going to move to a two diode circuit. So let's look at what happens if you have a two diode circuit. Let's look at example 2. Let's say if I'm having a, let me just withdraw it. This is an example in the textbook. You have to go through it on your own. This is a blocking circuit. If you actually see the actual transfer function. So let's say if I have two diodes back-to-back connected, and it's blocking the input and output, it's bridging the input and output. This connection, then let's look at what we have two diodes. So there'll be 4 combinations. There's a possibility of both of them turning on. There's a possibility of both of them off or either one of them. But how do you, not necessarily all the scenario will happen depending on the setting of your circuit. But it's the same thing is that we're expecting you to generate, we expect it to generate a transfer function also from -5 to +5. So let's say my Ving, you simply sweep your Ving and look at the Vout. So this will be -5 volt all the way to 5 volts. Okay, you want to draw the plot. So for this type of circuit, one of the problems is that it's very hard to start. How do you start? The starting point I find is mostly difficult for beginners. So the thing to do is that, of course, you start with the boundary. As we started here, we're assuming that it's starting at the most negative voltage, -5. So you start assuming that your Vin starts at -5, ramping forward. Okay, at -5, we're ramping toward 0. At this particular range, what happens is that if this is negative, you're assuming there's 2 branches of current. There's branch 1 and branch 2, I1, I2. Right? You're assuming that your first branch will not be on, right? Because this is more negative. So you're assuming that the diode will be off and only this branch will turn on. So the current will be flowing in this direction by supporting by this branch. So when it's more negative, you're assuming that I1 is 0, I2 is on. I should say D2. When D1 is off. And we're assuming that D2 is on. Okay? Because, sorry, I made a mistake. Should we turn it in this direction? The diode is in this direction. Oh, sorry. I should say my D2 is supposed to be off. When it's negative, you're assuming that your D1 is on and D2 is off. Because this is more negative. Let's place this. Okay? You're assuming that this branch is supporting current. It's negative, so the current is flowing this direction, but it's supporting current, allowing the voltage to be established on the output terminal. So if this is the case, you simply turn off this branch. Your circuit will look something like this. The equivalent circuit will be this. This is off, so this is open. There's only one branch. So the equivalent circuit will look something like this. A constant voltage model, because V1 is on. R1, R2. This is my output voltage, input voltage. So this is the same exercise as the previous one. It's just a different biasing, different direction. So we can actually construct our transfer equation simply based on this equivalent circuit. So your output will then become R1 plus R2, R2. And input, we'll add another voltage, we'll add a VD on. Okay? So we know that the slope of coming in from -5 will be R1 plus R2. We're going to use the same model. We're going to use the 1/2. So you simply insert this. The slope will be we know that it's starting from here, the slope will be 1/2. If I'm assuming R1 equals to R2, and the voltage level will be -5. So your V out at -5 will be 1/2. Let's say R1 equals to R2. -5 plus 0.8. And this will be 2.1. Okay? So this simply means that this particular point at the boundary is -5 minus 2.1. You get your starting point, you get the slope of moving. Okay? So there's an intercepting point. Let's see. You can actually project your intersecting point. Does anyone know where the intersecting point will be? When will this branch be turning off? This. If you're looking at the top, simply ignore branch 2. When does it turn off? Well, then you can actually use the equation to do the intersecting. But when does it turn off? Meaning that this diode turns off when there's not enough bias between the two. So this will then lower to 0, and this will be minus 0.8. So this is actually minus V1. Let me redraw this. So your slope will look something like this. So when it hits minus 0.8, what happened is then your D1 will then turn off as well. So this is true between where? I don't actually know, but based on this projection, I know once it hits minus 0.8, It's at the boundary. Okay? So based on this projection, I know that the mean is larger than minus 0.8. But lower than a certain level, we know that D1 is off. It's off, meaning that there's not enough voltage to turn it on. And what about branch 2? Even though this is minus, this is still minus sign, so branch 2 is still off. That is to say, I1, both I1 and I2 is 0. The branch 1, I1, and I2 are 0. That means that the current coming into the output current is 0. That means that I would then have VL equals to 0. Okay? So after passing the particular point, both of the branches are off. Therefore, we should be, give me 5 more minutes. So we should expect this to be a flat line. Until when? So what is the next turning point? You have to increase until there's sufficient voltage to counter the VB plus turning on the diode. Therefore, when? Correct, 2.8. So this is, let me write it down. This is minus VD on. How much does it need to turn on the second branch? This voltage is actually VD on. You need a VD on to turn on D2. And then to also counter, there's a bias voltage, which is 2 volt. So this will come to 2.8 volt. So all the way to 2.8 volt would enter zone 3. So there's zone 1 when D1 is on. Let me draw this. This is when D1 on, D2 off. This is when D1, D2 both off. Right? And when you start increasing your voltage, D1 will still remain off, but D2 will turn on. We're entering zone 3. So there's 3 different zones, and there's a turning point as we label on the curve. So on zone 3, what happened is that your circuit will then become looking like this. R2. Okay? So this is my VL. So your equivalent circuit in zone 3, this is when input is higher than 2.8 volt. When your input exceeds 2.8 volt, the underlying, the branch number 2 turns on. So that becomes my equivalent circuit. So this will be, your output will simply be, this will be VB, this will be VP on. So there will be 2 batteries in series. Therefore, your VL will be Vin minus 2.8 volt. So you get a slope of what in zone 3? The slope will return to 1, right? Because it's 1 to 1. So you get a higher slope. The slope will be 1, and it will then be 5, 2.2. Right? So once again, when you're drawing or constructing your transfer characteristic, transfer curve, the basic idea is that you start at the boundary and the edges and look at what the condition of each devices are. And then move along this, once you pinpoint a particular setting, you get a slope, you find out where the turning point is, and then you can draw the plot and find the characteristic at each zone individually. One of the key important things in having a transfer function, assuming having the right transfer function, is that you can actually send in signals and expect a response. What I mean is that if I'm using this particular transfer function on the right, using that one as an example. So typically, this type of transfer function question comes in three parts. One is that you generate this transfer function, finding out the boundaries and finding out the turning point. And then generate the transfer equations. You can generate the transfer equations at each different zones. And understanding the different stage of diodes. The last part is typically the third part of the question is you should do this. I don't know if anyone would like to try this. So let's say if I give you an input, instead of having a DC split, if I'm giving a sine wave, okay? So if this is my input as a function of time, if it looks something like this, and it has a peak level of 3 volt minus 2. I can give you arbitrary peak levels. So can you draw your output as a function of time? What do you expect it will look like? Anyone wanted to try it? How don't you think about it? So you should be able to generate a VL as a function of time. Also, in this VL function of time, you should be able to find out its turning point. Its peak value, peak levels. For example, for peak level, let's say if I'm operating in plus 3 volt, what's supposed to be the level? If I'm at a positive zone, I should be in zone 3, right? In zone 3, entering that will give me a level of work. Well, actually, at this particular level, it will be only 0.2. When my peak level in the positive range is 0.2, and the negative range, you can calculate that on your own. You can actually calculate your minimum point. When I'm at minus 3, I should also write at a minimum level using the equation that was established on the top. Right? So once you have these levels, you should be able to get a curve. Will look something very similar to this. Your turning point is actually in the vertical axis, right? So I have two turning points. One is 2.8. The other is minus 8. So this simply means that it will only allow current to flow when it passes this. So before this, it will be a flat. And then it will raise at a rate, will come. And then it will be flat until it reaches minus 8. So in time scale, it will look something like this. Okay, so the yellow will then be your output. You should be able to generate this kind of plot. For example, if I'm giving you a pulse like peak level of 0.5 volt, what will it be? Let's say if I give you a signal, I'm doing the same exercise. Let's say and this is 0.50 minus 0.5. What do you expect your output to be? It will be a flat line. Ooh. So this is being blocked. The signal, that's why I'm saying this circuit is a blocking circuit. If your signal is low enough, it will block all of it. Only when it exceeds your boundary level, and you will see certain level coming out of your signal. So you have to get a sense as what does this transfer function imply in your operation, and what does it suggest in the time domain if you're given a time domain signal. Okay. So if you look at a third example, okay. So this is actually the example we're going to spend maybe 2 more hours on, which is a very useful circuit. So I'm going to just give you an example. What if I'm having a diode? It's very similar to that blocking circuit, but I'm just blocking in one direction. So this is called the rectifying circuit. If I'm only keeping one branch, and make it a simple. So what is this transfer function? I don't actually need to draw 2 complicated circuits for analysis. Is you expect that input-output relationship will look something like this. There's actually only 2 zones. One is that when Vin is smaller than Vd, you expect the current ID equals, this is zone 1, 0, therefore VL is 0. So you're blocking the signal on the dial. So what happened is that before, so this is 0.8 volt. So it should be no current flow. No current flow, therefore no voltage. In zone 2, so this is zone 1. In zone 2, what happened is that when Vn is larger or equal than Vd, which is 0.8 volt, your circuit will look something like this. So basically, the diode can supply any amount of circuit, any amount of voltage, any amount of current to sustain the following of this voltage, a constant voltage drop between the 2. So this will be Vn, yeah. So then you can get a follower. Slow. Okay? So if you have this transfer function, what does it imply if I give you a sine wave? That will make more sense when we look at a sine wave response of this rectifying circuit. It's called a rectifying circuit because this is the time domain. This is my input signal. So if you draw your input signal like this sine wave, let's say amplitude plus minus. Okay? So you also want to highlight the turning point. The turning point will be this. VD1, which is a turning point will be this, which is 0.8. So positive 0.8 will be the turning point. You draw your turning point and the intersecting point to this turning point will then signal the changes in your the difference between the signals. So your expect should be able to draw the output response. VL is a function of time. It looks something like this. When it's lower than 0.8, there's no current flow. And then when it exceeds, it will follow to a difference of 0.8 and then a drop down. And then when it goes down lower than 0.8 and even to the negative realm, it will then flatten out at 0 and goes up. So you're blocking the negative, that's how do you turn AC signal into DC signal, or just a positive cycle, allowing only half the cycle to pass. This is called rectifier. AC. So this is actually the first step of turning an AC signal into DC signal. Of course, you're going to do some flattening of the signal, but you want to make sure only the positive cycle passes. The negative cycles are being blocked. Okay? So let me ask you, before we start the quiz, let me ask you a question. So where does the voltage go? Where is the voltage? Where is the voltage? There's a difference between voltage. So where does the voltage drop? Is being applied. So remember, the worst case condition is this. This is 0, right? This is minus 3. So this is minus 3 volt. This is minus 3. This is 0. So it's being applied on the diode. This is more positive here. So you actually experience a VP of minus 3, which is VR, which implies that you have a reverse bias voltage being applied on the reverse of the diode. So the voltage is being dropped on the diode. It's being blocked by the diode. So the diode system. As I said in the discussion of breakdown, is that this is where it counts to sustain voltage. If I'm giving you a pulse of like 1,000, you should be able to sustain 1,000 when it's off. You want to make sure that it's off. Otherwise, it will not be rectified. See, there's a voltage difference. The negative voltage is being dropped on the diode. So the main purpose of the diode is to sustain this voltage. So we're going to talk about, when we talk about rectifying design, is that you want to make sure that you pick the diode, have high enough breakdown voltage, otherwise the circuit wouldn't work, it will break down. Let's say with 10 volts breakdown voltage, you're applying 12 volts, and it will then allow current to flow, even in reverse directions. Okay?